Hi everyone, it is a great pleasure to introduce Annalisa Barla. She's in signal processing and machine learning, especially for biomedical data, and today she will talk about Python in medicine, especially for the analysis of temporal data.
Okay. Should I stand somewhere, or Luca? Should I stand somewhere?
No, the phone is.
Okay, good afternoon, everybody. It's actually, Vanessa could give the talk in my place because it's mostly her work. What I'm going to present today is what we are currently doing on the analysis of temporal data. It's, as I said, mostly the work of Vanessa, Veronica, and Federico, joined with Gabriele Arnulfo, who is a colleague of us, and Lino Nobile, who's a doctor in Gaslini, in the Gaslini Hospital. I would start from contextualizing what we do in the context of biomedical large-scale data. When thinking about data in the context of biomedical data analysis, we despise using the word big data. It's mostly not big, so it's large scale, and that's sufficient. Usually because when you're dealing with biomedical data, you won't have the opportunity of measuring more than hundreds of patients. If you're lucky, thousands of patients. What you usually do in the context of biomedical data instead is having lots of variables. If you think about genomic data, the genome in a human, the genome is composed of 3 billion variables, 3 billion bases. So the opportunity is you get to measure lots of things from one subject, but you won't have the opportunity of measuring the same amount of subjects. So from the statistical viewpoint, this is already an issue. It's gonna be better. There's a projection. This work is from 2015, so it's a bit old already, but it was proposed in the sort of an estimate of what's gonna happen in the genomic in the genomic data context. So the projection in 10 years from 2015, so 8 years from now, is 7, sorry, I can do the math, I promise, is the fact that, well, social media are right now the source of like big data, or the so-called big data. What we expect is that the fact of technology advances are allowing us to measure genomic information easily, in a fast way, and it's becoming cheaper and cheaper. Therefore, we expect to sort of store a large amount of data in a few years from now. So it may become a big data problem, but right now it's large scale, and it's already, and that's why from the statistical viewpoint, it's particularly interesting. Okay, moving a little bit, I would like to narrow down the attention from biomedical data to time series data, which in the context of biomedical data is becoming more and more popular, because time series now are easy to collect because of wearable devices, for example. So we wear watches, iWatches, wearable devices of any sort, and we are able to track how many steps we take a day, or how far we go, if you're running or walking or anything. And also with the new watches, like the iWatch, right now, the last edition of it has proposed a way to actually measure the heartbeat very accurately. And this is one thing. So time series analysis is becoming more and more popular, especially in the biomedical context. It is an opportunity if you think about time series data in the context of molecular data. They allow shedding a light on complex phenomena. So especially in the molecular context, understanding why some disease occur over time, like tumors, which are like the most complex, one of the most complex diseases studied, is very important. So time series are really a hot topic into the context of biomedical statistical analysis. Not just for science, not just for research, but also for industries. Okay. Okay, I'll make a confession. So this talk is sort of an excerpt of a talk that I gave at the EuroSci-Pi conference in Trento a few weeks ago. So I will pinpoint why, for example, we chose to use Python as a tool for developing code in this context. Well, first of all, because we are lazy and we like to stand on the shoulder of giants. And in that respect, Python offers lots of tools and libraries for doing stuff and the stuff that we care about. Therefore, especially we are dealing with structured data, and Pandas is a really great library for doing so. And we, at some point, we have, and I'll go into the details of it, we go through a signal processing, heavy signal processing phase, therefore using libraries that are already there and curated is really convenient. And lastly, we do machine learning on a daily basis, therefore we really adopt scikit-learn and all the deep learning libraries available. Okay. The next step, and we are trying to make an effort on it, is going towards providing doctors, the doctors we collaborate with tools for visualizing stuff. So the last bit is sort of communicating and being able to communicate the results of our analysis to people that are not necessarily familiar with the algorithms. Okay, first of all, well, data are messy, data are not perfect, data are noisy, and usually, oops, sorry, they come in different formats. They are not interoperable. They are very, very messy. So in our context, we don't assume we are prepared to spend lots of our time doing data cleaning. So data preparation and cleaning is not fun, and that's why using libraries that allow us to sort of import easily and do stuff easily on the data is very important, because it's really a time-consuming effort, and we sort of, I think I would estimate, we sort of spend half of our time thinking of cleaning data rather than focusing just on the fun part, which everybody would assume would be designing algorithms or designing new methods. But that's the sort of, if you want to do a hands-on sort of science, we are prepared to do that. Okay. Oops. I thought I skipped this. Is this the right version? Okay, sorry. No, it's not. Okay, sorry. I am skipping this part of the presentation. Well, just to comment a little bit, after data cleaning and data preparation, the data exploration part is a part of our daily life. So it's instead of we sort of investigate if it's easy to understand if there are patterns in the data, and that's what this library is about. Sorry. Okay. But the big question is, okay, how do I make sense of data? And well, we all live, or most of us live under the umbrella of artificial intelligence. We can cast our research into the artificial intelligence, under the artificial intelligence umbrella. But what I am going to talk about is machine learning. We are all familiar with that. So machine learning, I like this definition, which is very broad, but I think it's pretty accurate. The idea of machine learning is giving the computer the ability of learning and sort of predict what's going to happen without being explicitly programmed. So we don't have to take into account all possible cases before taking a decision. And that's very convenient, especially when dealing with this kind of data. you want to be able to sort of sample all the possible patients of one disease. So we have to sort of generalize and learn from the data you have. Okay, so we are trying to build models that are statistically robust and are able to predict and behave well on unseen data. At the end of the day, and this is sort of what this is very accurate as well. At the end of the day, it's just a pile of linear algebra, and that's what it is. Machine learning is still a very broad term, but especially today, I will just pinpoint to a few methods that we are studying and working on, and they are really living into sort of a standard category of machine learning methods. So basically, it's regularization methods, so learning from a few examples in high dimension, and we rely on regularization methods. And as we are in a large P, small n scenario, so we have more variables than samples, we are sort of we have to make sure that what we think it's a solution of our problem is stable and robust, and therefore we have to sort of resort to resampling strategies, and therefore being able to compute fast and resorting to high performance computing is the other key ingredient to solving the problem. Okay, so I won't talk and discuss any deep learning method. It may be interesting. It is interesting, especially in biomedical environment, in the biomedical context. It's very popular when dealing with imaging, medical imaging analysis. In the example I will comment, it's still early to think about modern, say, machine learning methods. So just to wrap up a little bit, we are in the context of learning from examples. We have signals. This is the example from music, but we have samples from epilepsy data. I will comment it briefly in a minute. We do some signal processing, and we extract features from the signals. And as this is a supervised problem because we have signals and someone tells us something about the data. So we have data and we have labels. We extract features, and then we propose sort of a learning method that is able to produce a statistical model which predicts if, say, in this case, the audio signal is a classical music, jazz, or rock. Okay.
Can I ask a question?
Sure.
So if I provide something that is completely different kind of music, do I get some information that's not?
Yeah. In this scenario, in this paradigm, you will get an answer, and it's going to be wrong.
Is one of the three?
Yeah. This is a very simplified version. You can have multi-class, or you could say.
No, I was more thinking of something that it's so
wrapped
out of the way from the.
In this particular case, you will get an answer which is none of it. In probabilistic models, for example, you could get low probability of being either of the three cases. So in that case, maybe you would get like a low probability, and if you set a threshold, you would sort of get that it's none of the three classes that you learned. But so to be exact, it depends on what choose you have here. But in this simple example, most likely you get a wrong answer. Otherwise, you do some methods like one-class classifiers, or like that learn from one class, and they are aware that the rest of the world aside. Okay. Feature extraction. What I mean by feature extraction is signal processing in general. So we have signals, and as I said, it's going to be, in this case, in the example that I'm going to describe, is stereo electroencephalography from epilepsy patients, but you could have any signal, and you think about it as a one-dimensional signal over time, and what you could do is represent it in a different way rather than the time series that you have. So this is a pretty standard procedure in signal processing. One example which is very state-of-the-art is using, for example, the Fourier transform. You could get from out of the signal, you could represent it in terms of its Fourier components. It's convenient. It is convenient because it's compact. It's a compact version of the same amount of information you have over the time series. And what you get is you store, instead of storing the entire signal, you store the coefficients. So you know that these are the coefficients of, so these are the weights of cosine and sines or whatever, and that lets you approximate the given signal. So one thing is you get to have an array version, so a vectorial version of the time series you have at the beginning, and with more complex functions, like instead of using Fourier, you could use wavelet transform or other kind of transforms. What you could enhance is some aspects of the signals. For example, some properties of the signals in terms of the Fourier, the frequency components, or how the frequency varies over time. And that's what sort of the feature engineering part is about. In the standard machine learning pipeline, this is the second step, say, after noise and data preparation and so on. So the preparation of data is, how do I decide to transform my input signal into something which is enhancing the properties in order to build a better classifier and predictor in the last part, which is the machine learning. So it's very sort of, there's an arbitrary component in this phase. We decide that the representation is based on Fourier or wavelets or whatever, and it's very arbitrary. Modern machine learning is something else, because the aim is to combine the two parts. So the new approaches trying to mix and find the best representation of your data together with the best predictor. But it's not what we're discussing today. Okay, so after the processing part, we get to have an array of numbers, which is the input data in a different form. So we still maintain interpretability. We know that these are the weights of the Fourier components of the signal. Therefore, we can sort of look at the data and then say maybe this component is more important than the other component for some reason. And then interpretability is another sort of a key part of the problem. And then what you could do is you have more than one signal. You have one signal for patients or one signal for subject. So any signal is your input data, and you transform it in terms of variables. The variables are now the coefficients, or in our schema, the coefficients of Fourier transform. And what you do is you collect all the data you have. You have data, and you end up having a matrix. Each line is represents a different example, and you have a supervised problem. So, sorry about it, you get to have labels as well. So each line is a transformed version of the input signal, the raw signal, according to some feature preprocessing part, and then you have the labels. And the goal is always the same. I got to build some function that takes into account as inputs the examples and is able to predict what's going to happen. Is able to classify disease from healthy subjects and so on and so forth. We can represent it in a two-dimensional fashion because we are not able to depict anything more than 2 or 3 dimensional, but really it's a high-dimensional problem. So the goal is I'm going to infer a classifier that's able to sort of predict well on the data that I get and the unseen data. Okay, just one other key ingredient, and I'm going to start with the last slide, which are sort of discussing the examples we are working on. Keep in mind, we are all familiar with the machine learning schema, but keep in mind that we allow functions to be not perfect on the training data. We are aware of the fact that we are not able to sample all the space. We won't be able, by definition, to do that. Now, even Google Photos is able. Google is not able to sample the image space in terms of images. We won't be able to sample the entire humanity in terms of any disease will take into account. And if you think of rare diseases, it's even worse. It's a statistician nightmare, so to speak. So we won't be looking for having a perfect classifier on the training data. So we are not looking for 100% accuracy on training set because it won't be able to generalize on unseen data. And therefore, it's the we are looking for compromises, and the regularization methods are all looking, it's a hymn to compromising between being perfect, so being able to predict. So the function, what I'm looking for is a function, which is the statistical model, which predicts on data and approximates one label. The way I measure the distance between what I get as a model and the labels is the way I measure myself as good or bad. And what I'm aiming at is minimizing this part, which is the fitness term, and also trying to have some property, keep some properties on the function itself. So the data fidelity term is usually combined with one or more penalty terms, which are sort of requiring some properties on the function. I could require smoothness of the function, then I would use an L2 norm. I could use an L1 norm and require sparsity of the function, or different combinations of the two, or even more complex regularization terms. So the key fact is we are looking for a generalization between being super accurate on the data that I have and being super regular, so having properties on the function. And sure.
Then you take this mean over F.
Yeah.
What is the space?
Yeah, that's another. This is a very imprecise slide. Obviously, I also usually limit the space of F according to some other rules, like it's going to be to leave some. It could be really a linear function or some other or polynomial function, so on and so forth. It usually I have to be able to have some metrics, and it's constrained as well. Okay, so the functional form of L and R could really be key to having an easy problem from the algorithmic viewpoint or a nightmare problem from the algorithmic viewpoint. As I said before, the regularization part is imposing some properties on the function, and what I have to do is, this is a parameter of the problem, and we usually select this parameter according to the data. So this is chosen, this is imposed, and the function f is the variable I'm looking for, and I have to choose the trade-off according to the data. Okay, now we get into the example, and then I'm done. Sorry if I'm taking a little bit longer than expected. What we are doing is one of the projects that we are working on, and it's a funded grant from Compagnia di San Paolo, is understanding focal epilepsy. Focal epilepsy is a disease that usually is can be sort of managed with drugs. except for a few patients, a portion of the patients that are called pharmacoresistant, so they are not responding to drugs. And so for them, unluckily for them, the only solution is to undergo surgery, and so the surgeon had to sort of take away the portion of brain which is not working properly in order for them to have a good quality of life. Okay, so before that, obviously, surgeons have to know exactly what to do, so they have to study exactly where the source of the malfunctioning is in the brain. To do that, they are able to measure the electrical activity of the brain, and what they do is they collect data over time in between two seizures and also in proximity of the seizures. And what they do is they look at the data, they visually inspect the data in order for them to understand which channel, so which part of the brain is really not working properly. And as they know the anatomy of the brain, they can sort of reconstruct the three-dimensional problem, and they know where they can infer where the source of the problem is. Obviously, this is very time-consuming, it's subjective, and these are doctors, so it's really very expensive, but they have to, and therefore, any solution that would ease their process is very welcome in the community. So what we are doing is dealing with data collected in this, with this goal. So we have Lino Nobili was able to collect and provide us with 65 patients. Electroencephalography is sort of a measure. It's very invasive because they have to implant electrodes into the. Sorry for being a little bit too graphic, but they have to implant electrodes in the brain. So they open the skull. So they implant these electrodes, and each electrode is sort of provided with sort of sensors. So it's about 15 electrodes per patient and 10 channels for each electrode. So all in all, they are measuring 150 time series per patient. So when I will use channel from now on. Channel is a time series, which is sort of measuring the electrical activity occurring in this part of the brain and so on and so forth. Okay. Depending on the patient, and the doctors decide where to put the electrodes. So one patient is different from the other, obviously, because it is. They are different. They are having different. They experience different symptoms, and because we don't expect the patient to have the same portion of the brain malfunctioning. Therefore, doctors are really deciding to implant the electrodes in one place or the other, depending really on the subject. Therefore, from the data analysis viewpoint, we already know that we won't be able to sort of compare one patient to the other. It's really one subject stands per se. Well, this is this is clearly, so the problem here is we have a few electrodes, and what we can see here, it's a portion of the time series that we have. The time series is acquired over 10 minutes in between seizures, so it's far away from seizures. And we see here that, well, the impression here, I'm not a doctor, so I wouldn't be able to interpret this plot too much, but this part is really sort of quiet, whereas we have more electrical activity on the last channels, on the last 4 ones. And therefore we can expect that that's what we are trying to look for in the data. Patterns of electrical activity into channels that are sort of able to predict if the channel is epileptogenic or not. Okay, so the task is basically what I said. We are trying to build a support system for clinicians and predict if the channels are epileptogenic or not, in order to be able to sort of support them, identify the epileptogenic zone, easy. And what we do, we resort to multitask, multiple kernel learning method. The idea, as I said before, is this is a method which is cast in the regularization method family. The only sort of real peculiarity is being multitask. It's multitask because, as I said before, we have different patients. We can't put all the data together and expect to build a function which is going to work on all patients. So this is a very, so this is a rough schema of what's going on. Each data matrix here is one patient, and we have sort of a three-dimensional data matrix. So each, here we have time, and here we have all channels for each patient, and we have n patients. Then we resort to signal processing, and in particular, we expect to have the behavior of the channel is going to be sort of we expect the channel to be normal up to some point, and then at some point something is going to happen, and the electrical activity on that particular channel, which is epileptogenic, is going to sort of behave differently from before. So we decided to resort to wavelet analysis because it's able to sort of enhance what's going on the frequency of the signal over time. So we keep sort of a time frequency representation of the signal. So that said, it's basically we have and the peculiarity of wavelets is we have different scales in order to sort of really emphasize what's going on. You could think of, you know, seeing, looking at the signal over 1 minute, 2 minutes, or a wider time range. The other key component of the protocol is we decided to build an algorithm which is able to sort of measure, compare, this data. And to do so, we are trying different measures. So the kernels in machine learning are really, you can think of them as ways to compare and measure the distance between data points. And we are choosing 3 different kernels. We choose to combine them, and these are chosen in order to emphasize, again, properties of the signal. And therefore, we resort to a multitask, multiple kernel learning algorithm, which combines these 3 measures. Okay, so I think I have another, how many? 2 minutes, 3 minutes? So I'm over time, okay, sorry. So we process the signal, we clean it up, we transform it with wavelet transform, and as I said before, this is a combination of time and frequency properties. And so if you look at this map, you have higher values coefficients when the color is when we have brighter colors. Well, this is because the wavelet library is better in MATLAB. And therefore, we had to now we are changing the code, but that's at the point of the publication, we had to use some MATLAB library. It's no panic. And then so we ended up learning a model which is based on the combination of some different measures of distance between the data for each patient. So each patient is treated differently, but we are trying to sort of you exploit all the information we get. And these alphas are the regression coefficients. So this is again a model, a linear combination of kernels which incorporate different measures, distance measures. We require, by the way, we also require sparsity on the solution, and that's because we also try to infer a model in understanding which portion of the frequency of the signal are more interesting in predicting the epileptogenic property. So I will just comment on the results. So we have these weights, and each band here is some frequency band. So the spectrum of the signal, the function that is predicting well is built upon a linear combination of kernels evaluated only on a portion of the signal. So what we observe is something that the doctors expected. That is the higher frequency, the higher frequency portion of the spectrum is more predictive of the epileptogenic property. Again, okay, so this is the output. So for each one patient, you could see the function is a probability. It can be a probability function, so we get to interpret the function as how likely one channel is to be epileptogenic or not. And it's a supervised problem because we have the label. So for each line is a channel, and the blue color stands for the label which we got from the doctors. So the blue color is non-critical channels, the red color is critical channels. And
what probabilities are higher than 1?
Not because this is an average over. It's in this question.
Repetition, but you have it's higher than 1 because the standard deviation is pretty high. But if you look at the bars, the mean value is lower than 1 in all cases.
Because it's not confidence interval. If it would be a confidence interval, it wouldn't go up. But as we are using standard deviation, this goes up, and it's. So the 50% chance is in between 0 and 1. So what we are happy to observe is that just a few channels that are color blue are reaching high, but they are all low. So they are all sort of over the 50 repetitions. They are all predicted as being non-critical, and the reverse scenario is occurring on the critical channels. I think I'm done, so I won't be bother you more. Sorry for being super long. While we went, sorry. Oh, I had another slide. Sorry. Okay, I stay here. Okay. So what we are doing is we are trying to sort of share the code, and all the code is available online on GitHub. And what we're trying to do is like to support reproducibility of the experiments is where we aim at sharing all things possible. In this context, for example, data are not shared yet. We hope we'll make data available, but in the context of biomedical analysis, it's still a little bit tricky sharing all data. So, code is available, data upon request sometimes. Thank you all for your patience. Thanks. Is
there any questions?
Luca.
Just a curiosity. So you spoke about your multiple kernels.
Mm-hmm.
So I really don't know anything about that. So just really a curiosity. So you chose a priori a bunch of kernels, and then you decide which were the best combination.
The choice of kernels is arbitrary, so we get to choose the methods we like, because we think upon the engineering of the features that those are the best kernels to enhance some properties. And the requirement is solving this problem, trying to find the F, for example, which is sparse. So it's going to be a collinear combination of the kernel components, a sparse linear combination. So I will interpret the result of in terms of the coefficients that I get, as I require sparsity, I will get some non-zero values and some null values. The null values are non-important and non-relevant for the function. Therefore, I interpret the other ones as the important and relevant parts.
So, okay, I'm missing only another bit. So, if you're using kernels, so basically you are destroying you're just adding n per n images, right?
It is an n times n.
No, it was just so the meaningful part are the coefficients. So if there is a coefficient which is higher than the other, then I just can point detection.
Yeah, but the sparsity is really non-zero versus zero. So
Okay.
sparsity means that I use some norms that are really canceling out, and they are not using some of the components,
Okay.
and therefore I build a function which is based only on a few components. Right.
So you, at the beginning, you had Python in the title.
See?
No, I have expected that Python is interpreted, so it's not very efficient to handle a lot of data. So where is the
advantage?
efficiency part?
The advantage is having, well...
so it's more the libraries that are doing the hard work but are not written in Python.
The libraries are not written in Python, definitely. But the convenience is that we have a pipeline which is very broad in terms of what it does, because it's really, first of all, you have to read the data, it's raw data format, preparing the data, blah, blah, blah. Then it's the signal processing, and then it's machine learning. The convenience is you could do that with the same language, and the language itself relies upon other languages. I mean, for the computational part, it's really not Python.
So you exploit more the fact that it's high level, and so it's easy to combine things.
Yeah.
Yeah. The number crunching is...
No, the number crunching is not. It's yeah, definitely. Okay. Thanks again.
Thank you.
Questo è il mio computer. Quindi